talk of the session. Nathan Cloos, are you ready? Go ahead. The stage is yours.
Yeah, so let me share my screen. All right, so normally you should sit. Okay, perfect. So I'm going to present you some of the work that I'm doing as part of an internship in the lab of Robert Yang at MIT. And this will be about the modulatory role of the prefrontal cortex when solving simple cognitive tasks. So recurrent neural networks have been used as a way to understand how the dynamics of a population of neurons can give rise to some useful computations to solve some tasks. And as an example, I will consider these results by Mente et al. From 2013, where they recorded the activity of the prefrontal cortex of monkeys during a contextual decision-making task. So briefly, in this task, we have two different sensory modalities. We have the motion of the dots and the color of the dots. And depending on the contextual cue, it is only one of the two sensory modality that is relevant for the current trial. So if we analyze the recorded activity of the neurons, we notice that it is actually low dimensional, and we can visualize it using some targeted dimensionality reduction methods. I'm not going to detail this now, so if you want, you can go to and check the original paper to have more details. But what is important is that when we train recurrent neural networks on the same task, we also observe these low dimensional dynamics. And so these trained RNNs have been used as a mechanistic hypothesis about how the dynamics of the neurons in the PFC are actually solving the task. So far, so good. But then my point is that when we are doing this, we are actually assuming that it is the prefrontal cortex that is implementing directly the computations. But if we take a larger picture and consider the fact that the prefrontal cortex is actually embedded inside a network of cortical areas, the function of this PFC might be different. So let me explain what I mean by that. So here we have assumed that the function, the role of the PFC is more transmissive. And by that, so here I have a small diagram to illustrate what I mean by that. So we have this, the prefrontal cortex that is represented by the box on the top. And we have different cortical areas that are depicted below. And so some of these areas are receiving the sensor inputs and others are producing the motor outputs. And in the case where the PFC has a transmissive role, it is directly computing the task response from the sensory information that it gets from the modules, from the sensory areas. And then it transits back the response to other areas so that they can produce the correct behavior. Okay? But this does not really capture what we know about the modulatory role of the prefrontal cortex. So in this case, the role of the prefrontal cortex is more to orchestrate and to organize the communication between the modules, which are themselves implementing and doing the work. So, and this idea is really not new. For example, there is this paper by Miller and Cohen from 2001 that argues that the role of the PFC is more modulatory. And so, in order to take into account the possibility of having a modulatory role for the prefrontal cortex, we have developed an RNN, a recurrent neural network architecture, that models the prefrontal cortex as part of a larger network of cortical areas. Okay, so I'm now going to describe this RNN architecture that we have developed. So in this architecture, we have what we call a cognitive system. So that's a simple recurrent neural network that models the PFC, and it has access to the contextual cues of the task. We then have a modular RNN that models the network of cortical areas. Some of the modules are receiving the sensory inputs and others are producing the motor outputs. And there are some interactions between each module of the modular RNN and the cognitive system. So there is also something special in this modular RNN, because unlike traditional RNNs, modular RNN, sorry, here the communication between the modules is implemented using an attention mechanism, which is inspired by this machine learning paper by Goyal et al. From 2019. And the motivation between this is to model the dynamic reconfigurability of the functional connectivity that we observe in the brain. And so thanks to the attention mechanism, the connectivity patterns between the modules can dynamically reconfigure itself. And we will see later that in some models, the cognitive system influences this dynamic routing between the modules so that it depends on the context. All right, so we now have this RNN model, and we can train it on a bunch of tasks. For example, we trained it on several reaching and decision-making tasks. And we can then try to analyze and understand what is the function of the cognitive system in this model. Okay, so the first analysis that we did is to look at how the task performance are impacted if we prevent the cognitive system from accessing the sensory information. So we silenced the communication from the modules to the cognitive system and look at how it impacts the task performance. Okay, so typically what we observe is that the performance will be greatly impaired. And so the model where the communication from the modules to the cognitive system is silenced, these models cannot solve the tasks anymore, which suggests that in these models, the cognitive system has a more transmissive role. So the cognitive system is responsible for computing the response of the task and then transmitting back to the output module so that it can output the correct response. And so when it doesn't have access anymore to the sensory information, the whole model cannot solve the tasks anymore. Okay, and so how can we have models where the prefrontal cortex has a more modulatory role? And so to have that, what we did is to add some constraint to this interface. And so I'm not giving all the details, but the idea is that we had a bit of a delay to this interface. And in that case, now the whole model has an advantage to use the modules to solve the tasks. And we found that using some constraint, now the model is able to solve the tasks without having the cognitive system to provide the correct solution directly to the modules. Because in this case, the cognitive system can only provide the contextual cue to which it has access. Okay, so this suggests that in some models, we have a modulatory role for the cognitive system. But to investigate that a bit more, we can look at the communication patterns between the modules and how it evolves during a trial. Okay, so now we will consider the contextual decision-making task that I described briefly on the first slide. And so in this task, we have three types of sensory inputs. We have a fixation cue that indicates when the model can output its response. And we have two sensory modalities, where the first sensory modality is the relevant one in the first context, and the second sensory modality is relevant in the second context. Okay, and we can now analyze the attention mechanism that is used for the communication between the modules in order to understand how the routing between the modules evolved over time. Okay, so here I have represented the query and the keys of the modules. So if you're not familiar with the attention mechanism, the idea is that the motor module here will output a query, and each sensory module has its own key. And the motor module will be attracted to the sensory module which has the key which is the most similar to the query of the motor module. So for example, during the fixation period, so at the very beginning of the trial, the query is here, the dotted arrow in black. That's the query of the motor module. And we see that it is the closest to the key of the first sensory module. That's why the communication at the beginning of the trial is from the first sensory module to the motor module. And as the trial evolves, the query of the motor modules will move and the keys also. And during the decision period, near the end of the trial, now the motor module is attracted to the second sensory module. And so here I've shown the attention weights for the motor module. And we see that at the beginning it is attracted to the first and then to the second sensory module in the first context. But in the other context, the motor module is attracted to the second sensory modality, which is corresponds to the third sensory module. And so here's the full picture. Depending on the context, the routing will change once there is the co-cue. And here it is really the influence of the cognitive system that makes this dynamic routing context dependent. Because if we remove the influence of the cognitive system, then we don't observe this anymore. So here's an illustration of how we can use this attention mechanism to understand how the routing and the communication between the modules evolve in a contextual dependent way. It was really on a simple task, but we can also do it on more difficult tasks, and also with more modules to have more complex routing. But yeah, this will be for some future work. So now, yeah, it's near the time of the presentation. So I will conclude. So I've presented an RNN architecture that takes into account the fact that the prefrontal cortex is inside a network of cortical areas, and that it can have either a transmissive or a modulatory role. And we have found that depending on the level, the amount of constraints that we add to the interface between the modules and the PFC, the role that it will take will change. And so some of our future work now involves looking in more details into the population responses in the cognitive system of our models, and try to see if we can observe similar population responses than the one observed in the brain. And we found that already in some of the models, even though the cognitive system has a modulatory role, we can observe similar population trajectories, which might suggest that the modulatory role is compatible with what we observe in the brain. All right, so this ends my presentation. I'm now ready to answer any questions you might have. Thanks.
I think I clap for everybody in the audience. Thank you very much for this really interesting presentation. Do we have any questions from the audience? If not, maybe I have a very perhaps naive question, which is this modulatory role that that you've kind of built in this. I'm not familiar with the attractor dynamic kinds of plots that you showed on the previous slide with these keys, but would the same thing happen if you had the context show up later after the sensory information has been presented? So you don't know which thing you have to pay attention to ahead of time, because it feels like the motor preparation is, maybe this is a naive question here, but does that make sense? That does it matter when you present which type of motor response or which type of sensory information you're going to have to attend to?
So yeah, so if I go back to this part, yeah, we see that really at the beginning, before that the stimulus are shown, the two keys of the two sensory modules that contains the sensory modalities are really, they coincide, so they are on the same line. And this is really the information about the context that will differentiate them. So that will make the one corresponding to the relevant input go towards the query of the motor module.
So it doesn't matter when the query is presented, whether it's kind of at the same time as any sensory information or afterwards. The contextual modulation that's driven by PFC could happen kind of any time in that chain. I see.
Yeah.
Great. Thank you for clarifying. I appreciate that. So if do we have any other questions at all? All right. Well, it looks like we're a little over time anyway for the whole session, but that's okay because we had an engaging set of 3 talks. So I want to thank all 3 of our speakers again for their really excellent presentations, and to remind everybody that we also have the Discord server for offline conversations if you have any questions that you didn't get answered here.